Continuous random variables and probability density. Continuous random variables are idealizations which allows probabilities to be computed by calculus. The basic idea is that probabilities are defined by areas under the graph of some function f. This f is called the density of x. This idea actually holds for both continuous and discrete random variables. For example, if x is the discrete uniform between the values 0, 1, 2, 3, and 4, then I can represent the distribution of x by this histogram. I think of this histogram as a constant function of value 1 over 5 for all x between 0 and 5. This function allows us to express probabilities involving x as an integral. For example, probability of x equal to 0 is the area under this curve from the interval 0 to 0.99999, and this is 1 over 5. Probability of 2 less than or equal to x less than or equal to 3 is the area under this curve from 2 to 3.99999. Probability of x is even can also be expressed as an integral, and this is 3 over 5. Here, I could think of x as truly being continuous on the interval 0 to 5, but I'm just rounding down this continuous x to the first digit, and therefore I obtain a discrete uniform of values 0, 1, 2, 3, 4. Similarly, if I now consider another discrete uniform, x, taking values 0, 0.5, 1, 1.5, and so on, up to 4.5, now I have 10 possible values, so the probability of x equals to any one of these values is 1 over 10. Now, if I drew the histogram with bars of height 1 over 10, then I have an issue. I no longer have the property that the probability involving x is the area under the curve. Therefore, I need to draw the histogram with bars of height 1 over 5. 1 over 5 here is not directly the probability of x taking a particular values, but rather I want it to be so that probability of x taking some value is the area under this curve. For example, probability of x equal to 0 is now the integral from 0 to 0.49999 of f, and this is a half times 1 over 5, and this equals to 1 over 10, as I wanted. This is also consistent with the discretization view. I think of x as truly being continuous. Before, I reported x to the first digit, rounded down. Now I report x to the nearest 0.5, also rounded down. As I take this discretization to infinity, I am reporting x exactly, with all of its decimal places. That is, I get a continuous random variable x uniformly distributed between 0 and 5. Its probability is the area under the curve. Because f is a constant, this expression simplifies to b minus a divided by 5. And this checks out with our intuition that the probability that a uniformly chosen number between 0 and 5 falls into some interval ab. This should just be the length of that interval, which is b minus a, divided by the length of the big interval, which is 5. Here is an exercise. Let x be a continuous uniform between 5 and 50. What is the density of x? Solution. Since x is uniform, intuitively this density should be a constant on this interval. Now, we need to decide the height of this constant. The area under the curve has to be equal to probabilities. So in particular, I need that the probability that x lies between 5 and 50, which is the integral from 5 to 50 of this constant, this has to be equal to 1. Solving for this gives c equals 45. So the density of x is 1 over 45 when x lies in 5 and 50 and is 0 elsewhere.